What is the last topic here in 4.3? It also has to do with second derivatives. It's the second derivative test. I'm thinking, oh, okay, there was a first derivative test. In the first derivative test, we were testing for local maxes and mins. Well, in the second derivative test, same idea. We're finding a different way to find local maximums and minimums. Obviously using the second derivative. How does this work? Okay, so notice I have these blanks in those sentences. So together we'll sort of kind of like try and fill in those blanks, or I'll let you kind of think about what it should be. You know, we'll fill those in. Say f prime of c equals 0. Okay, that's key right away. Let's say we've got a critical number, and it's the type of critical number where the first derivative is equal to 0. So we know that going in. All right, think about what that the implications might be. Right? If at that same place, the second derivative is positive, then what would that tell us about the point at CF of C? Would it be a local max or would it be a local min? And we'll do the opposite. What if at that point the second derivative was negative? Then the point at CF of C is a local what? Is it a local max or a local min? Okay, thinking about this, so we know the first derivative is 0. Let's kind of think about the first one. We're running out of time. We know the first derivative is 0. We know the second derivative is positive, right? If f double prime c is greater than 0. So what does the second derivative being positive tell us about the shape of the graph? Right, it's concave up. Well, if a section of the graph is concave up, then would it have a local max or a local min? Maybe you know the answer. You could draw it. Then let's think about the other one. We know the first derivative is 0. That's important. Don't dismiss that. We also know that the second derivative is negative. So that would tell us it's concave down. Well, if a section of the graph is concave down, would it have a local max or a local min? Okay, I'm going to reveal the answers. 3, 2, 1. You may have figured this out. Maybe it's the reverse of what you thought. This is like the one time where the positive negative, it ends up being the opposite of like our intuition, right? Like we would think positive is increasing, positive is concave up. But here, right, positive would tell us it's actually a local minimum. And negative, right? Negative, it's decreasing. Negative, it's concave down. But it turns out if you're concave down, you should have a local max. Why is that? Let's graph this. Not what I meant to do. Let me, just a quick like sketch. If you're concave up, right, you're doing this. And we also know, right, so we're somewhere here, but we also know that our first derivative is 0. So it must have been that this is f of x, right? So the second derivative is positive, concave up, but also the first derivative is 0. So it must have been a local min. All right, that's where first derivative of c equals 0 and where the second derivative of c is positive. Or, you know, the other one where it's concave down. This is going to have a local max. This is f of x. That's where the first derivative is 0. So that tells us it's at the top. The second derivative is negative, tells us it's concave down. So it's somewhere here And then this tells us, because that first derivative is 0, we know it was the point at the very top of it. So that's a local max. Okay. Again, maybe is the opposite of our intuition. But, if you think about what concave up and concave down, what that graph would be doing, then it becomes a lot more clear. Oh yeah, concave down is a max, concave up is a max. Right. All right, so it turns out there is one more possibility in the second derivative test. What if you plug that number c into the second derivative and you actually get 0? It can happen. That would tell us well, it wouldn't tell us anything, right? Our test would be inconclusive. Luckily, we do have the first derivative test we could fall back on. If that were to happen, we can still figure it out. So not a total loss. Okay. Let's use the second derivative test to find all the local maximums and minimums for this function here, r of x equals 1 plus 16 x squared. Minus 4x cubed. Okay, let's do it. Example, use the second derivative test. To find all local maxes and mins. R of x was equal to 1 plus 6x squared minus 4x cubed. Okay, so kind of how do we go about this? Right, the first step in that second derivative test was, or like not even the assigned steps. It's like the first thing it said was say f prime of c equaled 0. So we're gonna need a derivative, but like what beyond that? Find all x values where r prime of x here will equal 0. So it's like we're kind of finding the criticals, but we actually only care about the criticals where it equals 0. We don't care about the D and E type. Okay, so r prime of x looks good. 12x minus 12x squared, like it. Where does that equal 0? Right, factoring 12x, 1 minus x equals 0. So we know x could equal 0 or x could equal 1. Once we have these, then the second derivative test said, okay, now take those numbers. You know that the first derivative is 0. Now plug them into the second derivative to see if you were concave up, or if r of x is concave up or concave down there. And then you'll know, hey, if it's concave up and the first derivative is 0, and you can figure out, plug each into r double prime x. Well, we need to know what r double prime is. No problem looking back, that's 12 minus 24x. So if let's start with 0, not f, r double prime 0. Well, 0 in gives us 12. That's positive. If it's positive, is it a local max or a local min? If it's positive, that means it's concave up. Concave up has a local min. Let's also try it at 1. Plugging 1 in gives us negative 12. It's concave down, so that has a local max. We're not done yet. We want to find the y values, the r values, I guess. So now that we know whether they're maxes or mins, we can take those same numbers, plug them back into the original. I'll just recopy that, 1 plus 6x squared minus 4x cubed. Putting these back into the original to find their y values. Well, the 0 is easy, that's 1. The 1 isn't so bad. 7 minus 4 is 3. So we know we have a local min at 0, 1, and a local max at 1, 3. And there we go. Okay, so as you probably picked up at this point, you really gotta know what you're doing to decide like which derivative you're gonna plug a number into, right? So here we had to do it for, we had a few different cases. We needed to know the first derivative and solve it. We needed to know the second derivative in order to plug those numbers in to figure out what they were. Then we also had to plug them into the original to get their y values. You just want to be really aware of, why am I about to plug this number in to say the second derivative? Oh, because I'm trying to figure out the concavity. Well, when should I plug it into the original function? Well, if I want to know the y value so I can figure out the full point, right? Or when would I want to plug it into the first derivative? Well, if I want to know if the function is increasing or decreasing, that's the first derivative. So it takes a lot of awareness, and it seems like, oh, I'm just plugging numbers into different places and it's kind of like magic. And now I plug it into the first derivative. Now I plug it into the second derivative. Now I plug it into the original. Yes, but that is something that's very much understandable why I'm, why you would do whatever it is that you're doing. Obviously there's a lot of steps to these, and they compound on one another. In the end, the steps, right, like the increasing, decreasing test is really the exact same test as the first derivative test. The first derivative test just takes it a slightly different direction when you want to figure out what your maxes and mins are. The concavity test is like identical to the increasing, decreasing test, just with the second derivative. The second derivative test, this one here is definitely kind of its own animal. Although you still are finding criticals with the first derivative, you're only finding the ones equal to 0, and then you're plugging those numbers right straight into the second derivative to find if it's the local max or min. So this one really has a different feel, but the increasing, decreasing test, the first derivative test, and the concavity test all are really very, very similar to one another, or they take the same test and go in a slightly different direction. Okay, hey, I can't end this. I gotta take a look at this graph just really fast. Get rid of this. Okay, what was it? Y equals 1 plus 6x squared minus 4x cubed. There it is. And we can just go ahead and hover. Yep, 0, 1 is a min. 1, 3 is a max. And we can see the concavity. It's concave up. It's concave down. Very nice. Very nice. Okay. Hey, that's it for 4.3. It was a lot. These problems take time for sure, especially some of those second derivative ones that you'll see. But there you go.